Objective 9.3, Graphing General Rational Functions. In this objective, we want to be able to graph any rational function by identifying vertical and horizontal asymptotes, x and y intercepts, and any other key points that will help us to graph our function. So we will be building on what we worked on the last objective, but these are going to get a little more complicated and require a little more analysis. So, what are the steps? You'll notice on your guided note sheet that I have changed the order of the steps in the box. This is the order I am recommending that you do the different pieces in. Not that you have to do them in this order necessarily, but I think it makes more sense and is more consistent with what we were doing in our last objective. So we're going to start with step number 1 right here by finding the vertical asymptote. And it says the graph of f has a vertical asymptote at each real zero of the q of x, which if you notice here is the denominator. Now that's really just a fancy way of saying if we take our denominator, whatever that might be, and this whole mess here is really just the algebraic way of trying to represent any possible polynomial. So don't let that throw you off just because it looks like a mess. Okay, so if we have some polynomial in our denominator, if we set that denominator equal to 0 and then solve the equation, whatever values we get for x are the values where our vertical asymptote will go. Okay, that's what step number 1 is saying. So the first thing we're going to do is set our denominator equal to 0, solve for x, and those are going to be our vertical asymptotes. Step number 2 is this one. And in step number 2, we're going to find the horizontal asymptote. This is also sometimes called the end behavior asymptote, and I'll explain why in just a minute. But the horizontal asymptote is going to depend on m and n. And the m and n come from the highest degree in each of the polynomials. So m is right here and is the highest degree in our numerator. N is right here as the highest degree in our denominator. That's what they're referring to when they're making these comparisons. Okay, so if you look at your exponents and you see that the top exponent m is smaller than the bottom exponent n, then automatically y equals 0 is our horizontal asymptote. So the x-axis is going to be the horizontal asymptote every time m is less than n. If these two degrees, these two exponents, are equal to each other, then the line will be determined by taking a sub m over b sub n. So let's take a look at where those numbers come from. Those numbers are right here as the coefficients on the term with the highest exponent. So if you remember from last year, we called those the leading coefficients of each polynomial. And so this really boils down to just those leading coefficients. The fraction that they make, that is going to become the horizontal asymptote when the m is equal to the n, when the 2 degrees of our polynomials are equal to each other. If the top exponent is bigger than the bottom exponent, then instead of a horizontal asymptote, we have what's called a slant asymptote, because now the line that serves as the asymptote will not just be straight across like we've seen in our previous examples. This is actually going to be something at a slant. Now they talk about the graph's end behavior in this case, but we're not going to worry so much about that. Instead, what we want to know is that the actual asymptote line when this happens is the result of actually dividing the p of x by the q of x. And then we're going to disregard the remainder because it's not going to affect where the line is very much anyway. This is particularly easy to do if the q of x in our denominator is linear, because then we can use synthetic division as our way of dividing. Okay, so instead of horizontal asymptotes, we're really talking about end behavior asymptotes because they're not always horizontal. And the purpose of these asymptotes is to tell us what happens with the end behavior. What happens way out here on the graph and what happens way out here on the graph. It's not really telling us much about what's going on in the middle. Okay? So that's step number 2, finding the horizontal or end behavior asymptote based on what's happening with our exponents. Step number 3 now is back up here at the top. And for step number 3, we're going to find our x-intercepts. To do that, we need to have our answer, the y, the f of x, y, remember they're interchangeable, we need that to end up being 0. Well, the only way that we're going to get an answer of 0 is if we end up with a numerator that's equal to 0. So that's how we find the x-intercepts. We set the p of x, or the numerator, equal to 0, and we solve that. That gives us x-intercepts for the graph. And then finally, I'm going to add one more step that the book did not necessarily point out, but I think is another good point to find, and that is finding the y-intercept, because that's just a matter of putting 0 into your function and getting the answer. Okay, so 4-step process here. Step 1, find the vertical asymptote. Step 2, find the horizontal or slant asymptote. Step 3, find your x-intercepts. Step 4, find your y-intercept. Alright, so let's put this into practice. So here's our first example. We want to graph y equals 4 over x squared plus 1 and state the domain and range. So in step 1, we're going to find the vertical asymptote by figuring out for what number does x squared plus 1 equal 0. So again, x squared plus 1 is our denominator. We're setting our denominator equal to 0, and we're going to solve this. Now if we actually solve this, we're going to subtract 1 from both sides and then take the square root, which is going to be the square root of -1, or I. Since we're not talking about complex numbers here in these problems, that really means that there is no number that's going to make x squared plus 1 equal 0. So if there's no solution for the equation, then that tells us there is no vertical asymptote in our graph. For the horizontal asymptote, we want to look at the degrees. So what is the degree of our numerator? Okay, our numerator is just the number 4. So that makes this a constant polynomial, and constant polynomials have a degree of 0. Now what is the degree of our denominator? Well, here in our denominator, the highest exponent is a 2. So that makes the degree of our denominator 2. So how do these two compare to each other? Well, since 0 is smaller than 2, that would be the case where m is smaller than n. And we said when that was the case, then automatically the horizontal asymptote is y equals 0. So our x-axis will be the horizontal asymptote in this graph. Now moving on to intercepts. For the x-intercept, we need to set the numerator equal to 0. So I end up with an equation of 4 equals 0. For what number is that true? Well, again, the answer is none. So if there's no solution to this equation, then that means there is no x-intercept in our graph. And finally, for the y-intercept, we want to substitute 0 in for x. So 0 squared would be 0. The denominator would end up being 1. And 4 divided by 1 would get us 4. So using that information now, we want to graph our function. So we have no vertical asymptote, but we do have a horizontal asymptote, which we said was the x-axis. We have no x-intercepts, so we know there will be no points along this axis, but we do have a y-intercept at 4. So we'll plot that right here. Now once you have all of those pieces set up, then the rest of your graph is determined by points that you pick. So now we're going to set up a table of values. And because I don't really have a lot of information to go by here, I'm going to choose several values for x to make sure I really get a good picture of what's going on. And you'll find that because of the fact that our denominator has x squared in it, using opposite values will actually end up giving us the same answers. Because when I square negative 3, I get the same thing as when I square positive 3. So when I put negative or positive 3 in for x, I end up with an answer of 2/5. And so I can graph negative 3, 2/5, and positive 3, 2/5 as two different points that I know have to be on my graph. I do the same with the 2's. So negative 2 and positive 2 both give me 4/5, which would be right there. And then when I do the same thing with negative 1 and positive 1, I get an answer of 2, and so that's going to be like that. So the curve that I end up with in this case is a bell-shaped curve that is going to go through these points. It's going to peak here in the middle at 4, and then it's going to curve as it gets closer to that horizontal asymptote, so that out here on the ends of my graph, I know that my graph is getting closer and closer to that particular line. So this is the look of my graph for this function. Now in terms of domain and range, we are still going to use the same idea as from last objective, but we have to be a little more careful. So we still want the idea that domain will be affected by whatever the vertical asymptote is. Since we do not have a vertical asymptote in this case, our domain is going to be all real numbers. There's no restriction on what we can use for x here. So all real numbers will be our domain. Our range is still going to be affected by the horizontal asymptote, but instead of just saying y does not equal 0, when we look at this, we realize that there is nothing that is even below the 0. So our range really should be y is greater than 0, because the entire graph stays above my asymptote. So that would be our domain and range for this case. All real numbers for domain, y is greater than 0 for range. Alright, let's move on to example 2. In this case, we want to graph y equals 3x squared over x squared minus 4. And again, we're asked to state the domain and range. So we start the same way. We begin with the vertical asymptote by setting the denominator equal to 0. Well, in this case, we can factor this denominator because it's a difference of squares. So I can make it x plus 2 times x minus 2 equals 0. And if that's the case, then I know that my two x values are going to be x equals positive 2 and x equals negative 2. So in this case, I actually have two vertical asymptotes I will need to use. For the horizontal asymptote, I again go to my exponents. The degree of the numerator is 2, because that's the highest exponent I can see in my numerator. The degree in my denominator is also 2, because again, that's the highest exponent in my denominator. So when I compare them, I see that my two exponents are the same, which is the case where m equals n. And again, going back to our steps from the beginning, when m equals n, then the horizontal asymptote is the result of taking the leading coefficient from the top over the leading coefficient from the bottom, which in this case would really just be a 1. So 3 over 1 is just going to be 3, and my horizontal asymptote will be y equals 3. Moving on to my intercepts, for my x-intercept, what number makes the numerator 3x squared equal to 0? Well, hopefully you can see that that should be 0. And for my y-intercept, I want to substitute 0 in for x, and when I do that, I end up with 0 for an answer. So those are the pieces of information I'm going to use for my graph this time. My vertical asymptotes are at positive 2 and negative 2. My horizontal asymptote is at 3. And I have an x and y intercept right there at the origin, 0, 0. Now when I set up my table this time, I want to be able to figure out which of these sections my graph is going to be in. Now I already have a hint here in that I have a point here at 0, 0, which is in this section of the graph. But I don't really know what's happening over here or over here for sure. And I'm also not exactly sure what else is happening in the middle section, because here's where the end behavior asymptote comes into play. In this middle section, it is possible for my graph to cross the horizontal asymptote. So I could end up with a graph that looks cubic in this middle section with a shelf, or I could end up with a graph that looks parabolic, looks like a quadratic parabola in this section. I don't really know which one it's going to be until I test a few points. But because this is happening in the middle of my graph, it is okay for me to cross this asymptote. Out here on the ends, for my end behavior, it is not okay for me to cross the asymptote. So that's where the asymptote really comes into play, is where I'm looking down here on the ends to see what my graph is doing. But never, ever, ever do we cross vertical asymptotes. Those are absolute. You are never allowed to cross those. All right, so let's see what happens with this graph. I've chosen a few points here that will give me a couple of x's over in this section, a couple of x's here in the middle, and a couple of x's over in this section, so I can see where my y's will end up. And again, because we're dealing with x squareds, putting in a negative value or its opposite positive value is actually going to get me the same answer. So when I put in negative 4 or positive 4, I'm going to get an answer of 4. So I can graph those 2 points on either side of the asymptotes. Same thing with -3 and +3. Either way, I get an answer of 27/5, which is about 5 2/5, and puts my points right about there. Finally, in this middle section here, I've chosen -1 and +1, and those both give me an answer of -1. So I know my dots should go right there. And so now I can use these points as a guide for where my graph should go. My corner huggers are going to happen up here and here. And in this middle section, because of where the points went, I am going to end up with something that looks like a quadratic parabola that's opening down in between these two asymptotes. So this is the look of my graph for my function. As far as domain and range go, we again take a look at our vertical asymptotes. Since we have two vertical asymptotes, we need to exclude two different values in our domain. And for the range, since I do have graph that is above and below my horizontal asymptote, I will just simply say y is not equal to the 3, which serves as my horizontal asymptote. Okay? I know that's a lot of steps, but hopefully as you practice this and go through these steps over and over again, you'll get a little more comfortable with knowing how to proceed with these kinds of problems. And let's start that practice right now. Go ahead and take a minute to pause the video and work through this problem to see if you can graph y equals x squared over x squared minus 1. Don't forget to state the domain and range. When you think you have an answer, come back and restart the video to check your work. All right, so here's what you should have. First of all, we need to recognize that x squared minus 1 in the denominator can be factored. And from those factors, we would get x equals 1 and x equals -1. So this again gives us two different vertical asymptotes that need to be graphed. Next, we go with our horizontal asymptote. Our horizontal asymptote is going to be based on the leading coefficients in the numerator and the denominator, because our exponents on both the numerator and the denominator are the same. So the 1 here over the 1 here is going to give us a 1 for our horizontal asymptote. Next, I'm going to take my numerator and set it equal to 0, and that's going to give me an answer of 0, which also means if I put 0 in for x, I'm going to get an answer for 0. So the origin is once again a point on my graph. Now these are the points that I chose to use, the values for x that I chose to use. You do need to choose something in between these two vertical asymptotes. So even though they're not nice, easy numbers, you still do need to choose something to see what's going to happen. Is it going to be a parabola, or is it going to be a shelf like a cubic? In this case, it ends up being a parabola that opens down, and we end up with corner huggers in these two corners right here. For domain and range, our domain has to exclude the 1 and the -1, and our range has to exclude the +1 from our horizontal asymptote. All right, one more type of example. In this case, we have x plus 4 as our denominator. So when you set that equal to 0, we find that our vertical asymptote will be at x equals -4. For the horizontal asymptote, when we look at the degrees, we realize that the degree of the numerator is 2, and the degree of the denominator, since it's just linear, is 1. So when we compare them, our top exponent is bigger than our bottom exponent. And so that means that instead of a horizontal asymptote, we actually have a slant asymptote. Now, how do we get this y equals x minus 6? Well, we're actually going to divide this out. And because my denominator is linear, I can do this division using synthetic division. So I'm going to put the coefficients of my numerator, 1, -2, and -3 on the top. And then remember it's x minus c, so the c value is actually a -4 that I want to use over here. And then I'm going to divide. So that means bringing the 1 straight down, multiplying -4 times 1 to get -4, adding gives me -6, multiplying gives me a positive 24, and adding this gives me a 21. Now remember, when we do synthetic division, the last number out here serves as our remainder. And if you remember from the directions, we said we were going to disregard the remainder. So we don't really need this part of the answer. All we need is this part right here. And because I started with an x squared, my answer has to be 1 degree less, and so that makes this x minus 6. That's where this equation is coming from. Okay? If you didn't quite get that, rewind the video and watch it one more time. We're just taking the numerator divided by the denominator, and because it's linear, we're doing the division with synthetic division. Alright, moving on to our x-intercept. We want to know what number is going to make the numerator equal 0. Again, this is something that can be factored. Oops, try that again. So x minus 3 times x plus 1. Okay, and from those factors then, we can get positive 3 and -1 as values for x. So that means we have 2 x-intercepts in our graph. And finally, for my y-intercept, if I put 0 in for x, all of the x terms become 0, and I'm left with -3 over 4, or -3/4. So using that information, I'm going to start graphing. My vertical asymptote is at -4. My slant asymptote is the line y equals x minus 6. Since this is in slope-intercept form, that means I have a slope of 1 and a y-intercept of -6. So that's going to look something like this. -6 right there with a slope of 1. Now notice the 4 sections that I end up with from these two lines are not equal sections, but I do still have 4 sections. One of them being this little section right down here. And on this particular graph, that's a pretty small section. If I actually end up with part of my graph in that section, it's going to be hard to tell. So this may be a good time to adjust my scale so that things will fit a little better. So I'm going to change my scale to 2's. And I'm going to do it on both the x and the y axis. So now my vertical asymptote of x equals -4 is really only 2 squares over. And my slant asymptote of x minus 6 now crosses 3 squares down, but because I kept the scale the same, I can still go up 1 over 1 for my slope of 1. Now that gives me a little more room to actually graph something in this section if that's where my graph should go. Now continuing with the rest of my information here, I know I have x-intercepts at 3 and -1, so now I plot those in using my new scale, and I have a y-intercept at -3/4, so that goes about right there. So based on the information I have right now, I have a pretty good idea that part of the graph is going to be in this section right here. What I'm not sure about is what happens over on this side of my vertical asymptote. So I'm going to need a few points in a table of values, and I've decided to use -8 and -6 just because they work a little bit nicer. So with -8, I end up with a -19.25 as my y, which puts me right about there. Okay, and again, we're just trying to sketch these, so they don't have to be absolutely exact. And then with -6, I end up with a -22.5. And so these points got moved just a tiny bit, but you get the idea. And so now, because I have 2 points in this section, I know that part of my graph is going to be down here. And just for safety's sake, I chose one more value in this section. I chose a -2, which gets me 2.5 and puts me right about there. Okay, maybe up just a little bit more. But through that, I can approximate my curves. So I have one curve that's in this corner, and I have one curve that's in this corner. And you can just fit it in between the asymptotes. Okay, now this is the toughest kind of rational function you're going to get, and you won't get very many, but it does show up once in a while, and you need to know how to handle it when it does. Okay, but most of your problems are going to be more like the first two examples, where m is either less than n or equal to n, and you can set up horizontal asymptotes to help you graph your function. So I hope that gives you enough information to be able to go to your practice now. If you have any questions over the concepts in this video, please make sure you ask about it. I know it's a little bit complicated, but again, the more you practice this, the more I think it's going to become familiar and you won't be quite so confused about it. When you do finish the 9.3 practice and the rest of the 9.3 objective, make sure you get it checked off by me, and then you'll be ready to start preparing for the quiz 9A by working through your practice quiz 9A, which you can also get checked off when you're ready. All right, we'll see you next class.